Hi, nice to meet you everyone. My name is Sung-hyun Song. I work at FSI of South Korea. The FSI is responsible for the security of Korean financial industry. I'm research mobile security at FSI and I do penetration testing for Korean financial company. And I have experience speaking at several international security conferences in Europe and Asia. First of all, I want to explain why I became interested in Android runtime. Analyzing mobile app is a very important process for those who work in mobile security, like malware analysts or hackers. This is because it's possible to get a clear idea of how malware works or find vulnerability in your mobile apps only when proper analysis is done beforehand. There are two main ways to analyze mobile app. First, you can analyze the app if it exists as a file. In general, in Android, bytecode can be converted back to the original Java source code using open source tools such as DexJar. Another way is to analyze the app while the file is executed and loaded in memory. There is a dynamic analysis tool called Frida that can analyze the app during the runtime. So applications that handle sensitive information such as banking, gaming, and healthcare adapt to the security technique to protect themselves from the analysis and attacks. So if you try to analyze the app protected by RASP, you will be detected and blocked as shown in the picture here. This top picture shows the process of the decompiling to the original Java source code. Since the app is protected by anti-decompile technique, you are in trouble with convert it back to the original code. The bottom picture here shows warning message generated when it detect the app running the rooted environment or any attempt of dynamic analysis using Frida. So can we bypass RASP? Of course. In my thought, there does not exist 100% of security, but what I want is an automated, effective, and fast method. However, security modules are difficult to bypass because they are applied in multi-ways technique. So what's the problem? The problem is time. They also know that the RASP cannot define completely the attacker. The purpose of RASP is to annoy to the attacker as much as possible and increase the time required for the attack. There is no perfect mechanism and we are in state of continued help to fight. I want to get away from the endless fight between protection and bypass, just like Tom and Jerry. So over the past years, I have been thinking about how to analyze the app easily and effectively without being detected by RASP. Then I found two papers published in Unix 2021 and ACM 2016. The main subject of paper were about developing a framework that can dynamically analyze the app by modifying the runtime of Android. It was very interesting as it modified the OS to create an environment for the analysis. The advantage of this technique was that app could be analyzed without directly access the app's executable file or memory. But sadly, the paper were written for all the Androids. So I have to analyze the new runtime in Android 10. So I shift my focus from application to Android OS itself. That is kernel and platform. In the past few years, I started to analyze the Android source code and developing a custom OS. So I ended up building the Android OS by customizing the kernel and platform. The OS has built-in functions such as backdoor for privilege escalation, SE Linux bypass, Android verified boot bypass, and kernel memory access driver. I don't think I can cover all these, or I can cover all of these today due to limited time. So in this session, I will focus on presenting how I customize the runtime for the dynamic analysis of app. In this chapter, let's take a look at how Android's ART works. ART is an abbreviation for Android Runtime. ART can be called heart of Android and play a key role in loading app binaries, application memory management, apps execution, and optimization. However, it is not easy to analyze in depth how the runtime works in the restless version of Android. This is because the Android code size is huge, about 100 gigabyte, and various techniques, compiling, profiling, and optimization are also applied to the restless version of ART. In addition, Google has changed the Android runtime drastically each time a new version of Android is released. However, since all the code of app is interpreted and executed through the ART, if the attacker understands how exactly the app works on ART, attacker can still code interface, parameter, return value, field, and stack trace of the running function in the real time without using debugger or hooking tool. This slide shows the whole process of and how apps are compiled and executed in Android 10. First, when you try to install the app, APK file is downloaded to your mobile device along with the optimized profile data. During the installation, the profile information is used by AOT compiler to selectively compile the bytecode into AOT code for the functions that are commonly used by users. Second, when you execute the app, the ART checked whether the code of the running method is compiled or not. If the code is already compiled by JIT or AOT, it directly called the code, loaded in memory, and executed it immediately. If this code is still bytecode, the interpreter executed it and increased the method execution counter. If the counter of the method continued to increase and it become warm state, the profile information such as the number of the method execution is saved in the device as a file. While you are not using the phone but just charging overnight, the service compiled the warm method using AOT compiler and save it in file as AOT code. Next time, the method will be executed right away as AOT code from the beginning. And if the counter keep increasing and it finally become hot state, the method is compiled in the real time by JIT compiler and stored in the memory as a code cache. Then the code loaded in memory is executed as soon as the function is called. You see here, ART has various state and of code and complex structure. This time, I want to check the code flow in ART at the code level. This is the code flow that analyzes the execution process in ART. Here, compiled code called the bytecode, and bytecode called the compiled code, and bytecode also called the bytecode. I think it may not be easy to understand the whole process at once, but if you focus on the code execution aspect, there are two parts in the whole picture where the code is executed. The first part is compiled code, which call ART quick invoke stop function through the invoke function in ART method. This function invokes the execute and the compiled code. The second part is bytecode, which called the execute IMPL function through the interpreter's execution function. This function converts bytecode into native code and executes it. All information required to execute the app go through these two parts. The information contained parameters, return value, code, course tag, and so on. In other words, if you watch ART method invoke function and the interpreter execute function, you can trace all code running on Android. However, there was one missing piece that we could not see in the flow. What is that? That is the process by which compiled code called the compiled code. So why is this code not shown in picture? I'd like to go back and remind you how compiled code is called. As I explained before, ART method invoke called ART quick invoke stop function to execute compiled code. Let's dig into more about this part. The invoke function of the ART method class called the ART quick invoke stop function. ART quick invoke stop function is written in ARM assembly code to boost the execution speed. This function has address of target function to be invoked and executed. This feature shows the code to get the address of the function to be executed. This part contains the address of the value entry point from quick compiled code, and this variable contains the address of the compiled code for executing function. Put this address into X9 and directly call the compiled code using branch instruction. Let's call this compiled code A. Then A directly call the address of the next function B, which is in compiled code. Again, B directly call the address of the next function C, which also exists as a compiled code. Unlike the call structure we saw before, you can see the directory call from memory to memory when compiled code called another compiled code. If this is the case, it's impossible to trace the code when compiled code is executed from the compiled code. In addition, since compiled code has been optimized a lot compared to the existing Java code, so it's tricky to extract the original code even if you access the compiled code. So what I did is to change the call structure so that bytecode was always called instead compiled code for target function. So I changed the ART method invoke function to stop executing compiled code and instead use interpreter to execute bytecode. In this method, ART method invoke function to execute the compiled code in the existing flow is not called. Instead, it forced to always call the bytecode using the interpreter. This allows you to trace the flow of the all function because they are all executed using interpreter. Furthermore, you can get original code more easily because the execution code you are getting is a Smiley code format. For this purpose, I customized ART to display all information by adding a trace feature to two functions, ART method invoke and interpreter execute function. This figure is a table comparing the stack trace before and after the call flow change in ART with the technique introduced in this speaking. This figure is divided into two results. Above is the stack trace result before changing the call structure, and the bottom is the result of the stack trace after the change. Before the change, the function that exists as a compiled code were called the call from function that exists as a compiled code. In this case, it was impossible to trace all function. In the result of the stack trace of the change structure, The compiled code cannot be executed in the ART method invoke function, and the bytecode is executed by calling interpreter. This chapter introduces a framework developed with the previously described technique. As I showed you earlier, the code has been added to the customized ART to give you trace log. Since the function running in ART generated huge data, I needed a way to filter out data for the effective analysis. So I added the configuration file to specify the information that I want to trace from the ART. This shows the structure of the configuration file. The first part is to set UID for your analysis. You need to specify the UID of the app you want to analyze here. The second, there is an option to output basic information of the function to be traced. If it's set to Y, it displays the information of the target function, such as parameter and the return value. Third, this is an option to display the core stack information of the function to be traced. If it's set to Y, it shows you core stack information of the target function. The display code dump option toggles the output of the code from the function you traced. If you set it to Y, then the smiley code is printed for the target function. Lastly, there are two options, include and exclude. If we want to track the specific function, put the name here in include. Then all functions that contain the string will be displayed. And if we want to remove some unnecessary function from output, specify keyword in exclude. Then the matching function will not be printed. I prepared two demos. In the first demo, I will show you how to analyze the Santander banking app. In the second demo, I will show you how to steal personal information and credential data from PayPal app that has been downloaded more than 100 million times on Google Play Store. In the first demo, I will show you how to analyze the Santander banking app. Let's take a look at the configuration file first. As I explained earlier, you need to first specify the UID of target app that you want to analyze. Second, there is an option to print stack, code, and argument, and then you can include or exclude specific function that you want to track in the output. First, you need to know the UID of target app to analyze. Okay, I just got a UID of Santander app, which is 10168. Let me put the UID in the configuration file and run the app to see all the output from the functions. You can see that all the executed functions are printed here. Let's open the configuration file again and add Android's default package function to the exclude section. I'm restarting the app. As you can see here, it doesn't show any default Android function, but just custom functions. You can look through all the information here. This time, I want to print out only selected function. Come in the HTTP client blah blah function. I will just copy and paste the function to include the section. And find another function to analyze, ARTAndroid blah blah function. I will just copy and paste the function to the include section. Finally, I try to find one more function I want to analyze. Come app fryer blah blah function. I will just copy and paste the function to include section. Clear log and let's restart the app to take effect. You can quickly and easily analyze your app by copying and pasting after watching. Now you can watch the execution of three functions written in the computation file in real time. This time, let's look at the return value and parameters of the target function. Now I'm going to set ARG option to Y. Great! So that arguments and return value can be printed together. You can see the argument and return value are displayed. Meanwhile, I just found an encryption function. AR Santander, Rio, and Banking Managers, Crypto Manager encryption function. This shows that the function takes plain text as input and output it encrypted. I'm just going to add only this encryption function to the watch list and change the option to show smiley code. I try to clear log. And as you can see, the smiley code of the encryption function is displayed in real time. And this framework gets strings, fields, and method using smiley code from resource and automatically translate it. Great! Even if it's protected by code obfuscation, the information can be acquired right through the smiley code without any extra effort. And finally, there is an option to turn on the display of the stack trace information. The stack trace is printed as soon as the option is enabled. Everything information is processed easily and quickly in real time by this powerful framework. So it makes your analysis really easy. In the second demo, I will show you how to steal personal information and credential data from PayPal app that has been downloaded more than 100 million times on Google Play Store. First, let's take a look at the output of PayPal. The option is set to Y to show all the functions and argument without targeting specific functions. As you can see, there are too many functions printed here. Sadly, the output flashed too fast to catch the necessary information in real time. I'm terminating the run. Now I'm going to redirect the logcat output to the file called log1sh file. Then I start the command. As you can see on the screen, my ID is fsec.or.kr and my name is Sunghyun Song, and provide a login password which is bracket 1 exclamation mark. Then login process begins. The login is a bit slower because there are too much information being written to file. It's not visible here, but a ton of information is being printed and saved into the file. Now the login process is complete. I'm going to open log1sh file to see the saved information. Let's find the password that I put earlier. Okay, here it is. You can see the password bracket 1 exclamation mark as a plain text that I was used for login. Then I tried to find my mail address, tcash@fsec.or.kr. I found my email address. Then I tried to find my name, 성현송. I find my name too. Then I tried to find my phone number. I find my phone number too. And there are many my personal information, my country code Korea, name, email address, phone number, my home address, and blah blah. And I found the information of the person who exchanged the money with me is also exposed. Name, partition home address, and blah blah. As you can see, using this framework, you can quickly and easily check which function exposed personal and credential information, even if the app has strong code obfuscation applied. In conclusion, I developed a new analysis framework by analyzing and modifying the structure of ART. This tool is very easy, effective, and powerful. Thank you for listening. If you have any question, please contact me on Twitter or email. Thank you.